Consider a process for the milk derivatives. A single machine does the work. The orders to be processed by this machine are so structured within this table. Here we have the example. So as you can see here, we have three different milk derivatives: yogurt, ice cream, and cheese, from different customers, as you can see. And the order weight is so different from one order to the others. The customers has been working with us since 2003, 2001, and 2010. So it's like a kind of seniority. We will suppose that we are in 2020, so it will be 17 years with us, 19 years working with us, or 10 years. So the question will be, what's the position for every order? Will be order named number 1 the first to be produced? We don't know. We will see. Our intention is to serve first large, heavy orders. Why? Because the manufacturer policy leads us to serve large orders first. But then these heavy orders will be weighted by the seniority of the customer. So how long they have been a customer for us. So the manufacturer policy states that senior customers must be served first. So we will gather this information together in order to give the preferences of the problem, of the optimization problem. Every product type change, from yogurt to cheese, from yogurt to ice cream, from ice cream to the cheese, and the other way round, needs a washing procedure that lasts 2 hours. So as you may suppose, we want to avoid this washing procedure as much as possible. So that's why the orders of customers can be interlaced, but it is expected to avoid product change. So the interlacing of different products is strictly forbidden. What I mean with different products means different milk derivatives, so no product change. Finally, this information is misleading because we don't mind, for this problem, what's the process time for every milk derivative. We are expected to formulate the corresponding binary optimization problem according to the Matlab environment. So, first of all, we will define all the elements within the optimization array X. This optimization array will have 25 elements. The reason is that we have 5 orders to be assigned in 5 possible positions. So we have 5 candidates and 5 candidates for the positions. So the meaning for this array is the following. Let's take, for example, x1. x1 means will be order 1 assigned to position number 1? We don't know. As you may remember, every element within the optimization array can have a value of 0, false, or true, 1. But we don't know the values at the beginning, obviously. We need to solve the problem, the optimization problem. For example, x8, it's will order 2 be assigned to position number 3? We don't know. We will see. Well, the next question deals with the cause function of the optimization problem. As you may remember, in this kind of problems, the cause function is built by means of a linear combination on the elements of X, of the optimization array. The elements in the array named C are the values, or how good is to put every element within the optimization array equal to 1. So C contains the contribution of every element within the optimization array to the total value of the cos function. So in other words, tells how good is to put every element within the optimization array X true. So first of all, as you may remember, we have large heavy orders to be served first. So in order to say how good is the solution, we will take into account the weight in kilograms of, for example, the order number 1. As you may remember, the first element in X means the order number 1 being produced first. So, it's so good to make order number 1 to be produced first because it weighs 30 kilograms. And then, what about the weight? What about the seniority? It's 2020 minus 2003. So it's 17 years old. That's why I make the product. And how good is to put order number 1 in position 1? So 30 multiplied by 17. What's this number, this fraction in here? The first number tells how good is to make order number 1 be produced first. The second number is how good is to make order number 1 be produced the second. So as you can see here, I have like an artificial weight that it's decreasing. Can you see here? 1 over 1, 1 over 2, 1/3, 1 over 4, and 1 over 5. So that makes the difference, because for every element that belongs to order number 1, the weight is the same and the seniority of the customer is the same. So in order to tell the algorithm that is so good to put order number 1 the first, I will multiply this number by 1 over 1, and I will decrease this number as long as I'm decreasing in the position to be produced. So it's half good to be produced the second, 1/3 good to be produced the third, and so on. But this decreasing number is my invention, so it's not strictly formal. You can use the quadratic form, for example, 1 divided by 1, so 1 over 1, 1 over 4, because it's the square of 2, the square of 3, the square of 4, and the square of 5. That's why I call this the quadratic form. That makes a very huge difference between all the positions. The first and the second positions are so different, and as you can see here, the first and the fifth are far different one from each other. You may use, for example, the Fibonacci sequence, 1 over 1, 1 over 1, because, for example, it makes no difference to be produced first or second. Then 1 over 2, remember the Fibonacci sequence, one number is the addition of the two previous ones, so 1 over 3 is the next because it's the addition of 1 and 2, and 5 because it's the addition of 3 and 2. Or maybe forget about the first number, 1 over 1, 2, 3, 5, and 8, because 8 is the addition of 3 and 5, or whatever decreasing sequence of numbers. But this artificial weight makes the difference when an order is produced the first, the second, the third, and so on. So if I repeat this for all the elements of X, I will have the contribution on the final value for the cos function of every element. And as you can see, at the end, the last number, this, the corresponding C to X25, it's order 5 in position 5. How good is this solution? Well, order 5 weighs 50 kilograms. So that's the reason of this 50. How long More4Milk have you working with us? 2010. So 10 years old. 10 years of seniority. And what about 1 over 5? Because it's order 5 produced in position 5. That's why it's 1 over 5. And pay attention. Look at the negative sign. Why do I put a negative sign in front of all the cos function in order to make the negative? Because I want to maximize the satisfaction of the orders to be produced as soon as possible. To maximize this satisfaction cannot be done by Matlab, because Matlab knows how to minimize a function. So if you want to maximize a function, you must put a negative at the beginning. What about the constraints? First of all, let's have a look at the equality constraints. The equality constraints are like this, in a matrix form, because they are so linear. Let's have a look. Each order must be assigned to a single position. As you can see here, we are talking about order number 1 in position 1, 2, 3, 4, and 5. So, if I want to force one out of these numbers, and only one out of these numbers, to be true, to be equal to 1, and the remaining numbers equal to 0, I must put this. The addition of these 5 elements in X, they must be equal to 1. So that's the way I'm forcing only a single number equal to 1, because as you may remember, Xk can be 0 or 1. So I'm forcing that a single number within these first 5 elements in X will be equal to 1. So order 1 will be assigned in position 1, or maybe 2, or maybe 3, maybe 4 or 5, but in a single position, or to a single position. What about order number 2? It's the same, but the sub-indices are moved 5 positions. What about order number 3? It goes the same way, 4 and 5. Let's go to a different equality constraint, but it's also an equality constraint. Every position receives a single order. These are not synonyms. What I mean is, first I'm looking this table from the left, but now I'm looking this table from the top. What do I mean? Let's have a look at position number 1 in here. Here I have order 1 in position number 1, order 2 in position number 1, 3 in 1, order 4 in 1, order 5 in 1. So what I'm doing, I'm doing the sum of all these elements, because all these elements belong to position number 1, order 1, order 2, 3, 4, and 5, and I'm forcing that a single order is assigned to position number 1, because only one out of these 5 numbers can be equal to 1. All the rest will be 0. The same goes for position 2 here, position 3, 4, and 5 for these equations. What about the inequality constraints? They are also linear. So we can put these conditions, these constraints, under this kind of matrix form. So, no interlacing of products. Other 1 next to other 2 because both are yogurt, and other 3 will be next to other 5 because they are ice cream. Despite these are orders from different customers and these are orders from different customers. Remember, I want to avoid the washing procedure that lasts 2 hours and wastes a lot of energy, water and power consumption. So, let's remember for every moment the table, the original table. If other 1 is in position 1, other 2 cannot be in positions 3, 4, or 5. Why? Because there will be, if other 1 is assigned the first, then other 2 can be in these 4 positions. So other 2 can not be assigned here, not here, and not here. Because if I put them here, because this and this other are yogurt, here I will need not only 1 washing procedure, but 2 washing procedures. Because here there will be a different milk derivative. Okay? So that's why if by chance other 1 is assigned by the algorithm to the first position, other 2 cannot be in 3, 4, or 5. So how can I write down this? First of all, other 1 in position 1 is this, and other 2 in positions 3, 4, and 5 are x8, 9, and 10. So that's why I put x1 plus x8 must be less or equal than 1. Why less or equal than 1? Because I need to take care for the different combinations. They could be x1 plus x8 small or equal than 1. They could be 0, 0. So other 1 is not assigned to position number 1. And also other 8 is not assigned in position, other 2 is not assigned in position number 3. But maybe other 1 is assigned to position number 1, but then I'm forcing that other 2 cannot be assigned in position 3, because this leads to a double washing procedure. And the other way around, if other 2 is assigned to position number 3, other 1 will not be assigned to position number 1 for sure, because the inequality avoids this situation. So 1 is forbidden. And the same goes for all the remaining possibilities. I recommend you to stop the video and have a look at all these conditions. So now we have the cause function, we have the equality constraints, and the inequality constraints. How can you tell Matlab? As you can see here, I have all the weights within the array C, you remember, the cos function at the end is minus c multiplied by x. So this is the array C, that at the end is the cos function, because it's a linear combination. Then the equality constraints are stacked together, the first 5 and the second 5, as you remember. Each order must be assigned to a single position, and then each position will receive a single order. They are not the same. So keep this in mind. And then the no interlacing of products, or the 1 next to 2, because they are yogurt, and then no interlacing of products, or the 3 next to other 5, because they are ice cream. And remember, in order to build these inequality constraints, I have written down all the possibilities that are forced not to happen. All the possibilities that must be avoided. As you remember from the previous slide, I put all the conditions that avoid both variables to have a value of 1. And finally, I call the intlimprog.m. This is the Matlab function that solves this kind of integer linear programming problems. So this is f. This 1 to 25 means that 1 to 25, all of them are integers, integer numbers. Inequality constraints, equality constraints, these are the lower bounds, and these are the upper bounds for all the elements within the optimization array, within X. Because this tells the software that these numbers are integers, but not binary. If they are limited on the left by 0 and on the right by 1s, we are forcing that X will be binary. So this final slide shows the solution. If we apply this algorithm, we will get as a result that, as you can see, we change the customers, okay? So more for milk must wait until this moment, because both orders are not consecutive. But here we have the benefit that we don't have a washing machine, a washing procedure in the middle. We have a washing procedure here and here, but we have minimized the washing procedure. But here we had a washing procedure here, washing procedure here, and another washing procedure here. So that's the aim of this problem.